Nowadays, everything needs an electricity. Even the small part of our daily life needs an electricity. So, there is many ways to produce electricity. For example, combined cycle power generation. Let's go! Assalamualaikum and hello everyone. So today our group will give a short presentation or explanation video about combined cycle power generation. One of the most widely used technologies in modern electricity generation.
Bah. Combined cycle power generation plays an important role in many countries because it helps meet large-scale electricity demand while making use of available energy resources. Due to its effectiveness and reliability, it has become a popular choice for utility companies and power producers around the world. In this presentation, we will discuss the basic construction of combined cycle power plant, explain its operating principles, and analyze an example of a real-world power generation site. Without further ado, let's get started.
Wait. Not yet.
Oh, not yet.
Before we begin, let's take a look at our group members' introduction video first. Check it out. Alright, now you already know our group members. Let's start our presentation. Let's go!
Hello everyone, I am Ahmad, and today I will walk you through the basic construction and main components of combined cycle power plant or CCPP. The heart of the facility consists of three primary blocks. Gas turbine block. This includes the air intake, compressor, combustion chamber, and the gas turbine itself, which drives a generator to produce power. Major manufacturers include GE Vernova, Siemens Energy, and Mitsubishi Power. Steam turbine block. That steam then powers a steam turbine and another generator. This block also features a condenser and feed water pumps to recycle the water back into the system. Heat recovery steam generator HRSG. Instead of wasting the hot exhaust from the gas turbine, we capture it here. Using economizer, evaporators, and superheaters, the HRSG turns water into high-pressure steam. Cooling system, utilizing cooling towers and pumps to manage thermal energy. Electrical system. This is the brain and bridge of the plant, featuring generator step-up transformers, the switch rack, and the distributed control system DCS for protection and SCADA control. Balance of plant, BOP. These are the essential services such as the fuel gas system, water treatment plant, and fire protection. CCPPs are built in different configurations depending on the needs of the grid. 1x1 configuration. One gas turbine and one HRSG paired with one steam turbine. It's simple and easy to maintain but has a lower output power. 2x1 configuration. Two gas turbine and two HRSGs feeding one steam turbine. This is the most common setup worldwide because it offers a perfect balance of high efficiency and reliability. 3x1 configuration. Three gas turbine feeding one steam turbine. This provides massive power output but require much more complex control system and maintenance.
Now, let's look at how this system operates using thermodynamic staging. It works by stacking a high temperature topping cycle and a lower temperature bottoming cycle to squeeze the absolute most out of our fuel. First, in the topping cycle, ambient air is compressed, mixed with natural gas and ignited. The resulting high velocity gas expands through the gas turbine, spinning the first generator to produce our baseline electricity. Next is the magic phase. The exhaust leaving the turbine is still a blistering 600 Celsius. Instead of wasting it, we route this hot gas into the HRSG, which is heat recovery steam generator. The gas has up water-filled tube inside, boiling the water into high-pressure steam. Finally, in the bottoming cycle, this superheated steam is piped into the steam turbine, spinning the second generator for extra electricity without burning any extra fuel. The steam is then condensed back to water to repeat the loop. By recycling this waste heat, we successfully jump from 40 to over 60 thermal efficiency. To understand how this generator works, The turbine mechanical torque spins the internal rotor, which is an electromagnet powered by a DC excitation system. As this magnetic field rotates, it cuts through the stationary stator windings by Faraday's law of induction. This relative motion induces a high voltage three-phase alternating current (VHIC) in the stator. This electricity is then matched via grid synchronization and step up for transmission, pushing overall efficiency over 60%.
I'll be presenting the visual part of the combined cycle power generation system. In this section, I will show several pictures to help us understand how the system is arranged and how the main components are connected in a real power plant. First, we will look at the overall layout of a combined cycle power plant. This diagram shows the complete system from start to finish, where natural gas is used as the main fuel source. We can observe how the system is divided into two main cycles, the gas cycle and the steam cycle. It also clearly shows how energy is transferred from one stage to another to produce electricity more efficiently. Next, we will look at the gas turbine section. This is one of the first major components in the system. From the image, we can see the turbine connected to key parts such as compressor and combustion chamber. This section is important because it is where the initial power generation begins. After that, we will see the heat recovery steam generator, or HRSG. From the picture, we can observe that it is a large structure similar to a boiler system. Its main role is to capture hot exhaust gases coming from the gas turbine. Instead of wasting this heat, the system reuses it to produce steam, which improves overall efficiency. Then, we will look at the steam turbine section. In this image, we can see how steam is directed into the turbine system. The steam causes the turbine to rotate, which helps generate additional electricity. This shows how the second cycle of the system works together with the first cycle. In conclusion, a combined cycle power plant utilizes a gas turbine to produce electricity through gas turbine generator. The exhaust gases are then used to generate steam in the heat recovery steam generator, or HRSG. This steam is then converted into electricity in the steam turbine and steam turbine generator. The use of a combined cycle power plant increases both the total amount of electricity generated and the overall efficiency of the plant. Overall, the visuals helps us to clearly understand the structure, components, and real-world arrangement of a combined cycle power plant. Thank you.
Now, let's look at a real-world example located in Melaka, the AZHAN Melaka power plant in Alogaja, fully operational since 2022. It is officially the largest combined cycle power plant in Malaysia, generating a massive 2.2 gigawatts of electricity. This single site actually supplies about 10% of Peninsular Malaysia's total power demand. As shown on the screen, the plant uses the highly advanced H-class gas turbine. By capturing hot exhaust gas to run secondary steam turbine, it achieves a record-breaking efficiency of over 60%. It's a perfect example of how combined cycle technology delivers cleaner, high-efficiency energy for the country.